Sharing is not turned on. So I need to be given host powers, apparently. Hey, hello. Oh, my goodness, Doug, good to see you. It's been too long. How are you? Okay, let's see. Oh, I got to sign in before I can get my host privileges, probably.
I just made you go.
Oh, well, maybe I don't need to sign in. Let's see. Oh, yeah, I got powers now. Okay. Share. Is that, am I sharing properly? That looks promising. Okay, good. Okay. So should we wait for fewer people or just do it?
You can probably just go ahead and get started.
Okay, well, I'm happy to, I can just talk for hours on this, so I'm happy to have a conversation and interrupt me and ask me questions. I'm interested in making sense of what's going on under the hood in quantum circuits and quantum computers and quantum mechanics in general. And that's my angle, is in the quantum foundation side of things. So a lot of people, even in quantum mechanics, don't even really understand what quantum foundations is. This is how I like to describe it. I like to describe it in terms of, well, you can come up with the definition, but the way that I think about it is, suppose I was back in the 19th century and I had all these great laws of thermodynamics and they all worked fine. You know, heat was a fluid that would flow from hot things to cold things, but I wanted to go into thermodynamic foundations. I want to know, why do these equations work? What's going on? Why do these laws so successful? And so I would ask a foundations person in the 19th century, we would try to discover what's behind this, what's underneath it, what's underpinning it, right? And eventually they did, right? Eventually they figured out that it's molecules and atoms, right? And that explains, the explanatory arrow goes up here, right? The explanatory arrow goes from atoms and molecules to all this stuff. And if you can't see these slides, you guys can move closer here. But like, that explains the laws of thermodynamics. That's what a foundational person would have discovered and did discover in the 19th century. And then, of course, there were more consequences of that. And so that's kind of how I see quantum mechanics today, is I see quantum mechanics, like we have all this stuff that we do in the math. We have our wave functions and our operators and our calculations. We know how to do it all. And I'm asking these same questions. I'm like, well, why these laws and why do they work? And what I want to find is not what quantum gravity people are trying to find. They're saying, okay, this is fundamental, let's generalize it, right? Let's go up from there. That's not what I'm doing. That's not what quantum foundations does. What quantum foundations is actually doing is trying to go down, right? What's underneath the hood? Why do these laws work? What's going on? What are the fundamental quantities underneath wave functions and operators, right? And then if we ever found that out, then we could presumably have other consequences, right? And maybe they would look very different from what people imagine quantum gravity is going to look like, because especially if what's down here is something more compatible with relativity, something that lives in space and time, to explain why quantum theory works the way it does, then maybe there'd be a whole new path to reconciling gravity and quantum. Not the way that they imagine it happening now, where you actually take space-time and quantize it. Maybe that's the wrong approach. Maybe you want to start with something in space-time and build up from there. So that's kind of my research. The million foot view of my research is I want to know what's hiding down here. So I guess you might wonder, wait, what makes you think there's anything down there? I mean, a lot of people don't think there's anything down there. They think we got the fundamental level. We got the fundamental equations. That's the last level down. You know, it takes a little bit of hubris to think that, but a lot of people think it all the same. We've got to the bottom. We got quantum mechanics, and everything goes up from there. But there are a lot of reasons to think that there's hidden levels. The original Heisenberg uncertainty principle, the whole point of it was we don't know everything, right? We can't know everything at once. That's not how we think of the Heisenberg uncertainty principle today, but it's how it was originally thought of, as you can't know everything. And so there's got to be some other stuff that we don't know down there. In general, for all the classical physics, anytime you have probabilities, it means you don't know something, right? If you ever know everything, there are no probabilities. And here we got a theory of probabilities. That kind of tells me maybe there's something we don't know, right? Something down there. The experimentalists can't answer our questions of what's happening between measurements by definition. And so there's a lot of reason to think there's a area we don't know what's going on between the preparation and the measurement. We can't get in there by definition because we don't know anything until the measurement. So there's this whole big region of stuff that we don't know what's going on. And what was my last point? This quantum mechanics doesn't make any sense if you actually just look at the math of what's happening from preparation to measurement and you interpret it literally. It seems crazy. And I mean, you can do the math. You guys are all doing the math, I hope, and find out, well, if I set this up and I crank through the calculations, this is what I expect to see. These are the outputs I expect to see. These are the correlations, these are the probabilities, and you can predict them. But is there any insight as to what's going on in the middle, or is it just churning through some rules that we don't know why they work in the first place? And so I want to open this box. I want to see what's going on with it. Do you have a question? Or okay, so there's my pitch that we don't know everything and there's more to know and there's more we should know. But it's not a popular pitch. It's not. A lot of physicists will say, no, that's all wrong. We know that there's no deeper level. And some people will say we know there's no deeper level, or some people will say, well, what's wrong with just interpreting the math we're doing as being actually what's happening? And so people look at the, when you calculate a wave function and then you evolve it, right? And then you collapse it. People say, well, why can't that be what's really happening? Why not just read off the math that we're doing and say that's reality? Well, there are various arguments about that. There's the measurement problem, and there's this craziness of what the collapse means, and that why is it that when I learn about it, it collapses, but when the atom learns about it, it doesn't collapse? What's so special about me? And you get into all that stuff. But here's another argument I make, which is that there's another way to get the exact same outputs, probabilities, and correlations with this totally different math called the path interval. And it looks completely different. Like every intermediate step is different. And if you're just going to blindly read off these calculations and say that's reality, why not blindly read off these calculations and say that's reality? I mean, why is one better than the other? They both get the right answer. And so I wrote this paper with a former student who's now in a PhD program in Oregon, and pointed out that you can do it all this way too. And in fact, not only can you do it both ways, but they're kind of mutually exclusive black boxes. Like they can't both be right. And now you say, well, is this one right or is this one right? Or more likely, I think neither one's right. We haven't found the right way to think about it yet. We haven't figured out what's in the right black box. But if you're just going to argue that might as well take that literally, I could say, well, might as well take that literally. And neither one makes any sense for different reasons, but they're mutually exclusive. You can't think they're both right. You can't just say, let's do either one. One of them contradicts the other as far as what's happening in the middle. Yes?
But what makes them mutually exclusive?
Well, one interesting thing is that this is all done in Hilbert space and configuration space. This is done in space-time. You consider all the possible paths that a particle might take and all the things that might happen, and they're not in Hilbert space. They're in space-time. And then you combine them in this weird, crazy way and get the answer. So that's one difference. Another difference that we talk about in this paper is this case called entanglement swapping, where you have two pairs of entangled particles, and you take the middle two of them and you eventually measure them together. You do this for quantum teleportation and stuff. And the other two were not. And it actually, you get different viewpoints.
Okay, Gatorade.
Oh, here. somebody asked me a question or just talking. You get different viewpoints depending on whether you measure the middle ones after you measure the wing ones, or whether you measure the middle ones before you measure the wing ones. The conventional calculation, you discover that you get entanglement in one case and you don't get entanglement in the other. Here, you get exactly the same calculations. So either one of the stories is wrong here and this one's right, or both the stories are right here and this one's confused and thinks that in one case you have entanglement, in one case you don't. And it's kind of funny. I mean, these W's in space-time shouldn't matter, right? If you measure it in space-time, if you measure it like this, you measure the middle two first, then you conclude these are entangled. But if you measure it like this, you measure the middle two last, you conclude these aren't entangled. But it shouldn't matter because what determines simultaneity should be a reference frame anyway. And so this idea that the order should matter is like this old legacy of the fact that quantum mechanics is non-relativistic, and you think of wave functions as being moments in time. We shouldn't even think that way, right? We know better. We know space and time are all one big chunk. So I like to think in terms of the whole history, the whole W's and V's. So there's one argument. There are other ones in the paper that these are mutually exclusive. Yes.
Quantum mechanics isn't built to this, and doesn't happen to those.
That was the nice discovery that Feynman found, that when you do quantum mechanics with the path integral, it's easier to relativize it. Yes, and you got quantum field theory and relativistic stuff this way. But then you stop thinking of states at all. You start thinking of histories. And now what happened to your wave function? Right? Well, now where is my wave function in the path integral? It's like nowhere to be found. Unless, of course, you break it up into little infinitesimal time chunks and can recompute your wave function at every step and recover this old story, but then you kind of lose your path integral account. So I don't know. You can, if anyone's interested, you can Google entanglement in the path integral and see why I think these are in disagreement. I actually think they're both wrong. I think neither one of these make any sense. And I want a story that makes sense in space-time. So here's my space-time story for entanglement experiment. You create some entangled particles at some source. You eventually measure one of them at this point in space-time. This is like space, and that's time, right? So eventually one of the particles makes its way up here, and you measure one of them. Eventually another particle makes its way up here, you measure another one. You have these settings you choose. How am I going to measure each one? You have an outcome, capital A, capital B, and you get all these predictions of quantum mechanics that say, if I set my settings, my source, and these A, B, C, I put these inputs in, it predicts this joint probability of the outputs. And it works. It works. You get the right answer. But then you say, well, what just happened? What happened in the middle? And quantum mechanics is completely silent as to what's physically happening in the middle. It'll give you this math you do, but the math doesn't live in space-time. It lives in Hilbert space or configuration space, and there's no map back to space-time. And there's actually no localized story at all of what's happening in the middle. And so if my question is what's happening in the middle, quantum mechanics doesn't help me. It doesn't tell me what's happening in the middle. And for you guys thinking about quantum circuits, let's look at the same story in a quantum circuit. Why can't I ask what's happening on every quantum wire here? So you got some generic circuit. You got your 1 qubit gates, your 2 qubit gates. Why can't I say, okay, what's happening on this wire? What's happening on this wire? What's happening on this wire? I want to know what's happening on these individual, maybe these are heavy ions, or I don't know what your favorite architecture is. You know, think of them as a bunch of spin 1/2 particles, maybe. Right? What's happening on that particle? What's happening on this particle? It's the same question. What's happening in the middle? And we actually, that's a really good question. So why can't we talk about what's happening on each individual wire in a circuit like this? I mean, how would people answer this rhetorical question here? Why is there no description of what's happening on each wire? What do you think?
The wave function has to describe the whole entire the space.
So yeah, the wave function at this point might be in, if this is 100 qubits, it's in some giant Hilbert space. You need 2 to the 100 complex numbers to define that, right? And you only have 100 wires. So you would need to put a lot of numbers on each wire if you wanted to do that. And it seems kind of crazy. You add one more qubit and you have to double the number of numbers on each wire, which is kind of weird. Here it's fine, right? There's no problem talking about what's on this wire and what's on this wire, right? So there's no problem here. It's once they start getting entangled, you say, well, you can't do it anymore. Right? So you can do it here. You just, oh no, now I can't do it, now I can't do it. But like, wait. What happens at the end? What happens at the end? I measure it, I get a bunch of outputs. Is this really any essentially different from this? Here I got a bunch of inputs. Here I got a bunch of outputs. It seems like if this is easy, why wouldn't this stage at least be easy? But everyone's convinced that no, there's no way to do it. And the big argument, like if someone was going to make a generic argument, there is no way to make this happen. You cannot possibly come up with a hidden variable account of what is going on these wires because what? What would be the classic response there? You can't do it because of, well, okay, but I don't want to try to measure them. I just want to try to know what they are after the fact. Say the circuit runs, put a bunch of inputs. Okay, I can't see what's happening. All I can see is at the end, I get these outputs. And I asked the question, what just happened? What happened on each wire? And I want to describe a hidden variable story of what's happening on each wire. And a physicist would tell me, no, you can't do that.
Because you'll change the outcome by looking at all those wires in between. Say.
If I look at them, right. But what if I just want to compute it? What if I just want to model what actually happened on every wire? Why can't I do that?
Bell's theorem.
Well, the interesting thing about probability is once you actually learn the outcome, there are no more probabilities here anymore, right? Because now I know for sure this outcome was spin up, this outcome was spin down, this outcome for the one run of the circuit, the probabilities seem to have vanished. Maybe there are still hidden probabilities inside, but at least once I know the outcome, there are no more probabilities. I know everything. So why can't, at that point, why can't I go back and deduce what happened? Like if I go to a football game and I show up at halftime and I see the score on the scoreboard, I can infer something about what just happened in the first half, right? Why can't I do that here? Why can't I infer anything about the past when I learn the outcome? That would be the standard response. The standard response is you can't do it because Bell's theorem. But if you really drill into, so that's the main thing I want to talk about. Say, why do people think that you can't do this because of Bell's theorem, and why actually can you do it? And there's hope. There is actually hope to get a localized account of what's happening on these wires. I don't have it yet, but this paper we published 4 years ago now in Reviews of Modern Physics basically explains why there's hope. And it basically goes through, wait, what does Bell's theorem say? So what Bell's theorem says is it says, okay, let's just imagine a generic model of these experiments. This is the most generic model you can imagine. What sort of mathematical framework would you need to describe that model? And one of the issues with Bell's theorem is something called locality, right? The idea that is this theory local? We'll define that in a moment. But the moment you start talking about locality, it means that you're talking about things that live in space and time. You can't talk about locality of the color red. You can't talk about locality of things that don't have a space-time description. So right away, we have to imagine that some of the parameters in our theory are associated with space-time, such as, something hidden on these wires. There's something at this time, at this space, there's something going on there. Or in this story, there's something happening right here on this particle path. There's something happening at that place and that time. So we just imagine there is something at a place and time. And I'm going to build a model that has some of those parameters, right? So what is that model going to look like? it's gonna have things like electric fields or magnetic fields or things in general relativity or events or, something on this wire, something over there, something happens over there, right? I'm going to talk about things that live in space and time. Bell called them local beables as opposed to observables. So not things that you observe, the things that just are, like an electric field. It's just there, right? It's a beable. It's not an observable. And I want some of these things to be in my model so I can talk about locality. There might be other things in my model that are not one of these local beables. The total energy of a system is an example Bell gave. It's not a beable, right? It's not like here or there. It's just this number I use to calculate it. That's not a beable. The wave function is not a beable. The wave function doesn't live in space-time. It lives in Hilbert space. It lives in configuration space. It's this 2 to the 100 complex number thing. I can't talk about where the wave function is in space-time. The wave function is not a local beable. And then I want to model the phenomena I see in the laboratory. So I have inputs. Remember my little a, little b, little c, things I can control. And then I get a bunch of outputs with probabilities. And what I want a model to do is say, okay, which are the things I can control and which are the things that I can't. So everything I can control, I'm going to call an input I, and everything I can't, it's a Q. It's not an I. It could be hidden. It could be measurable. It could be an output. It could be just some secret thing I don't know about, but it's not an input. There's a difference between things I can control and things I can't. And what should a model do? A model should do this. A model should give me a probability distribution. If I set my inputs I to be some values, it would say those other things you can't control should be this value with these probabilities. It's just a function. It's like if I put I in, I get a probability distribution to Q out. That's a model. There's a model. So what is quantum mechanics? Quantum mechanics is a model that says if I put these inputs in, say this setting, I want to measure this setting, I want to prepare the source this way, and I want to measure this one in that orientation. I put these inputs in, it's going to tell me I expect these pairs of outcomes to occur with these probabilities. That's what quantum mechanics does. Any model that explains experiments has got to do this. Any model has got to have this structure. But now, Bell said, well, let's fill this in. And since quantum theory doesn't say anything about it, it's hidden. These are hidden variables. Something is happening in here. I don't know what it is. Let's model it. Let's add that to the model. So how did Bell say to do this? Well, first of all, he imagined that some models are local and some models are non-local. He needed to formally distinguish that in his proof. And he's like, I'm going to assume that I have a local model. So what do I even mean by a local model? Here is a cone in space-time. And it seemed natural to Bell, and it seems natural to me, that if I know everything that's happening in this region S, then that's about as much information as I can ever get about what's going to happen in region 1. If I learn something new that happens over here, that shouldn't change my probabilities I assign region 1. If I learn about an outcome here or a setting here or anything over here, given that I already know S, I shouldn't have to update my knowledge of 1. So in other words, he said, what a good local model would be is that if my model can predict parameters in region 1, in some region of space-time, anything I learn over here is completely redundant. It shouldn't change my probabilities, given that I already know everything going on in S. S it's a conditional, Bell called it shielding or screening off. There are these things called Markov blankets that are a formal way to put this. But the idea here is conditioned on what I know here, learning something over here shouldn't change how I'm thinking about region 1. That's a local model for him. Here's the math. The math is basically saying that if I have a model that says, oh, I have an input in region 1, I1, I have an input in region 2, I2, a setting, and I want to predict what's going to happen to these parameters in region 1, Q1, given that I already know the parameters in region 2 and the parameters in region S, that should be equal to just throw out knowledge of what the settings I2 are. I don't have any I2 over here, and throw out knowledge about what parameters can Q2 are. So this is a mathematical identity saying that the model should predict the same thing for these two, and that is a local model. And this seems reasonable to me. It seems like this is a good mathematical definition of locality. If a theory doesn't obey this, what does that mean? It means that when I turn a knob here, I update my assessment of what's happening here, even though I haven't learned anything new about S. So that's like a magic action at a distance, right? Or maybe it's faster than light communication from 2 to 1, or something, the wormholes opened up from 2 to 1. Something weird has happened to bypass region S. That seems kind of weird to me. So let's call that Bell's screening assumption. You can't prove Bell's theorem from that assumption, it turns out. You need one more assumption. You need this kind of a causality assumption. You have to assume that the future doesn't matter in a certain sense. Here's the specific sense it can't matter. If I have a setting here, like an input that I can set, and I have a prediction of what my my parameter G here in the past should be, given I set my setting F to be whatever it is, then it shouldn't matter. If I recalculate it for a different setting, I should get the same value here. This is basically saying that what I do in the future, my settings in the future, shouldn't have any impact on what these parameters are in the past. And that also seemed like a reasonable assumption to make. So he makes these two assumptions. He makes Bell screening assumption, the locality assumption. He makes this no future input dependence assumption, and he calls this package local causality. It kind of makes sense, like it's local and it's causal. He used this. People don't use this phrase anymore, but he used this phrase. And then from these two mathematical definitions, he proved a mathematical theorem. And he proves this theorem, and the theorem says that if I try to fill in this gap here with hidden variables, lambda, and I enforce these two conditions, the Bell screening assumption and the no future input dependence, so local causality, then there is no model that's going to agree upon. No model. It can't be done. And this should have been big news. Nobody paid attention at the time, but it was very big news, and it's now been given a Nobel Prize for the experiments to check this, that you could try to add things in here, the things I care about, right? You can try to add them, but as long as those two facts are true, even if there's no lambda at all, you can't get rid of Bell's theorem by saying, oh, there are no hidden variables, I've solved the problem. It doesn't solve the problem. Now there's nothing here, right? And so what's there? Nothing. It doesn't explain anything.
Professor?
Explain the experiments. So what's the conclusion? Unfortunately, the conclusion people draw is, well, let's not even worry about this. That's the wrong assumption to draw, because I'm worried about this. I wonder what's happening in the middle here. I think the right way to look at this, and the way Bell looked at it, is say, well, one of these must be wrong. When you make a proof by contradiction, like if these things are true, I've just made a contradiction. There's no model to explain reality. That can't be right. There's got to be a model to explain reality. So therefore, one of these things must be wrong. That's the way to think about it. One of these assumptions must be wrong. And that's why when you hear people say Bell's theorem proves that nature is non-local, what they're saying is this must be false. That's what they're saying. This is false. There's no way this can be right, because if it were, you could prove Bell's theorem, and we know Bell's theorem is violated by nature.
Professor?
Yes. Hey.
Hey, how you doing? How you been? Good.
Okay.
So I wanted to ask, you're putting it in terms of locality and also like causality.
Yeah.
Normally, I've heard it in terms of locality and like realness, in the sense of like, they have properties prior to measurement. So
Yeah,
where does that
local
come in?
reality.
Because that's normally how I've heard
Local
it phrased.
realism. Local realism is a phrase that appeared in the literature sometime between Bell and now. Bell never used that phrase. He used local causality, or just locality for short. Local realism appeared at some point, and it kind of convinced people, oh, actually the two assumptions are locality or reality. That's not mathematically true in any sense, but a lot of people have this in their mind. Oh, I just have to give up reality and then I'm fine. That doesn't save you, because once you give up reality, what's there left to be local if you don't have no reality left anymore? So actually, there's papers written about this, that there's no coherent way you can give up reality and save locality. So it's not even true mathematically. Mathematically, these are the assumptions that go in the proof. It's locality and causality. Absolutely. It's not, there's not a reality. I guess the only reality assumption you could imagine is to assume that there is some reality here where you say, okay, I'm going to give that up. I'm going to throw out lambda. So there's no lambda anymore. And now there's still no local causal model to explain quantum mechanics. It doesn't help you. So you've got to give up one or the other.
So you're saying that you couldn't have a situation where you maintain locality, but they don't, even if you introduce the idea that these objects don't have properties prior to measurement, that still wouldn't be enough to solve this?
Yeah, people claim that, oh, you just remove lambda and you're fine and you're solved, but that's a lie. That's not true. It's not true mathematically. It's not true logically. What's left to be local if I pull everything out of reality, right? It's not local, certainly, if what's happening is there's nothing here and magically these correlations are appearing between these 2 points. That's not local. So there's no sense in which you can recover locality without having something there. So no, you can't save locality by giving up lambda. But there is a way. There is this way that people don't pay attention to. What's the alternative? What we got to give up local causality, and everyone's like, oh, therefore Bell screening assumption's wrong. What's the alternative? Give up causality. Yes. And so why not? Well, people don't like that, but that's really more of a gut instinct, I think, than a logical argument. So let's go through it here. If you do want to save locality, there is only one way to do it. It's not by giving up reality. It's by saying that whatever is happening in here has to depend, in really a causal sense, about how I choose this setting A here in the future and how I choose this setting B here in the future. So if the hidden parameters depend on the future inputs, and it's not no future input dependence, that's what NFID is. It's future input dependence. Now the future matters in a sense. And then actually you can save locality. That's the only way to do it. Yes.
Some way that you can tie that into the propagators. I mean, there must be some sort of.
I think there is a link to path integrals there. Path integrals, anyone who's done one know you fix the future and solve for the past. The problem there is it gives you the sense that the future is constraining the past, and maybe it is, but it's not the bright sense, because what is constraining the past and the path integral are these things, the outcomes. The outcomes constrain the past, but that's always true. Remember my football example? I walk in, I see the outcome of the football game. I know what just happened. So learning the outcome constrains what must have just happened. That happens all the time. That's not weird. This is different. This is the setting. That's weird. The setting that I go in, freely choose whatever setting I want. I'm not modeling that. If that's can correlate with the past, that's new. That's beyond just the outcomes. So this is weird. The people, and this is accurately be a retrocausal model. If you break no future input dependence, and you have a future input dependent model, I think the right word is retrocausal, in that somehow something is causing the past. Okay, so the one unavoidable fact is that any model of these phenomena has to violate local causality. There's no way around that. That's just a mathematical fact by this definition. Right? It's a precise mathematical definition of local causality. So you basically have three choices, right? You can violate locality. Maybe you have action and distance. Maybe what's communicating this information is the wave function. That's kind of the standard story. The wave function links everything together, and magically it makes these correlations happen. And it was called magic by Schrodinger when he named entanglement. Or maybe they're tachyons, something faster than light, zooming from region 1 to region 2 faster than you can get. Or maybe wormholes are opening up, right? People postulate this. That's all type 1. So everything in there is type 1. There's type 2. You violate the other one. The future inputs matter. That's what I'm interested in. Violate the no future input dependence. I guess you could have a type 3 where you violate both. Arguably, actually, this violates both, because if you have tachyons going faster than light in one reference frame, they're going backward in time in another reference frame. So arguably any like wormholes or tachyons or anything to do physical faster than light influence are also have a retrocausal influence. So actually, maybe there are more type 3 models than I like to give it credit for, but there are at least 3. Brendan, is that a new question or an old question?
Yeah, no, I noticed in the previous slide you put not super determinism or deterministic.
That's
So
good.
I wanted to ask about that because my understanding super determinism does require some type of future input thing, even if they're sneaky about it and don't talk about it too often.
Yes. Here is
So what is the difference specifically between this retrocausal picture and then super determinism? Because it seems like they're both based on the same fact.
Here is the causal model I'm describing, that you have lambdas that are dependent on your settings. And this is really the only proper way to think about causation as far as I'm concerned. So you choose a setting, A, B, C, and you say what's correlated with that setting, and that's caused by your setting. And so this is the model I'm describing, that somehow the lambda in the middle is caused by this. There are other people that say, no, this is really what's happening, is there's some event in the past that is causing lambda, causing my settings, causing Alice to choose her setting and causing Bob to choose his setting. And that's what correlates. They're all correlated here. They're all correlated here. And the reason they're correlated here is direct causation. The reason they're correlated here is common cause. This is super determinant. That's the difference. The difference is what's causing what. And notice what is being caused here is your setting choice. Now that there's all sorts of problems with that. One problem is you have to model Alice for one thing, and nobody can model Alice. Another problem is that it is not really an input to the model as I see it. I mean, when I say this is coming in, where is that coming in from? It's coming in from outside my model. I'm not modeling Alice. What quantum mechanics doesn't model Alice, right? Quantum mechanics does this. It says, given my input, what's the probability? If you want to reproduce that math, you can't go to superdeterminism. Superdeterminism doesn't reproduce that model. It says, okay, I can't put A as an input. I have to choose A as an output of what Alice chooses, and I'm going to model Alice. There's all sorts of reasons why that is problematic, but that's the difference. The difference is the causal structure of what I'm
But
talking
doesn't superdeterminism, doesn't it posit future input? Like you would have on that diagram, you would have a backwards arrow pointing the path. Because I've seen, like, for instance, Sabine Hassenfelder, who's loves this idea. She's referenced that she would have.
Sabine Hassenfelder likes to use the term superdeterminism to incorporate both what I call and everyone else calls superdeterminism and what I call retrocausality. She likes to lump them together and call them all superdeterministic. But then impressed, she will say, okay, there is a difference. In fact, she's now written a paper on this, specifying the difference. Where was that? Here. This difference. Wait, where was I? This difference. She'll sort of grant that there's a difference here. This is what everyone other than Sabina pretty much means by superdeterminism. This is what people mean by retrocausality. You see the backward arrows here. There are no backward arrows here.
Right.
So that's the difference. Good. Thanks for asking that. Bell himself on this slide I mentioned got confused by this. He said that when he started to think about this model, he started to worry about being fate. He started to worry about being fated to do things. And that's this, right? You're fated to choose A. You have no choice because you're a puppet caused by the Big Bang to choose this setting. And so he got confused between these. He didn't have this causal language, causal model terminology that was developed later to think about. When he wrote the text, he clearly was had the sense in mind that A was a cause, and that somehow tripped him up, this conflation. Okay, what time is it here? We got a little time. Let's start here. Why don't people like type 2 models? I'm sure you can imagine a few reasons, but some people think if this is true, if you have a model of lambda, and lambda is a function of A and B, it's not just a function of C. C is the past cause, right? A and B are the future causes. Then you're like, oh, you got time travel. You can send messages back in time. You can't though. Anyone see why you can't? If I could control lambda in the past. No, that's not it. It's that lambda is what? Well, sure, but why can't tomorrow? Why can't I turn A and cause lambda now and send a message back in time? Why isn't that a message? Let's remember what lambda is here. What is lambda? Lambda is all the stuff I never knew in the first place. Lambda is all the hidden variables. They're hidden. You can't send a message something is hidden, right? So there is no paradox you can make because lambda is hidden by quantum uncertainty. You can't get in there to measure it by definition because you're not measuring it yet. So it's safe. It's safe from paradox. It's weird. Oh, it's totally weird, but it's not paradox, right? If you could send a message into a closed box yesterday and no one's allowed to open the box till after you sent the message, that would be weird, but it's not a paradox. You can't like order somebody to kill your grandfather or whatever, right? If they can't open the box to read it. Yeah. That's right. And lambda's hidden. Lambda's hidden. That's the crucial thing. It's because it's a hidden variable that makes it safe for time travel. Or it's not time travel. There's no protocol for measuring. It's hidden. If you can't signal, you're not getting any deviations from predictions of quantum mechanics. The other argument people make is they say, oh, but we know that time flows forward, or the second law, entropy increases. But remember what I said at the very beginning, all of that story about entropy now has a fundamental microscopic story that we understand much better. We understand where this notion of entropy came from. And at the fundamental level of particles colliding, there are no time asymmetries. And so we've discovered that the reason the second law exists, the reason there's this time asymmetry in the second law is not because the laws are asymmetric, but because, first of all, entropy is assuming you have partial knowledge of the situation. It's not assuming you don't know everything, or there's no entropy. And you don't need an asymmetric law, you just need asymmetric boundary conditions. You can get the second law from a special Big Bang, from, anytime you have a special thing on one side and not a special thing on the other, you get a direction. So it's the boundary condition on the universe that makes the second law, not the fundamental physics. If the fundamental physics is time symmetric, that actually lends credence to future input dependent models. Because why not? Why couldn't a future constrain the past in the same way the past constrains the future?
So you're saying it's symmetric boundary condition. I heard you mention the Big Bang.
Yeah, the Big Bang can explain the second law.
Yeah, so what if we had a Big Bang and then a Big Crunch? Those are technically.
So people have wondered about this. Maybe if there's a big crunch that's the time reverse of a Big Bang, would entropy start to decrease right before the big crunch? Maybe, it would actually, if it were the time reverse. You would get a future boundary condition. You would get exactly the sort of thing I'm talking about here. So sometimes when I think about this retrocausation, I think in terms of future boundary conditions as a constraint on the past, on the present. Something is going to happen, it's a constraint on the present. And then entropy goes the other way. If I told you in 1 minute ago, all the air in this room was in that corner, you would statistically say, oh, by now it's filled the whole room. If I tell you 1 minute from now, all the air will be in that corner, then the only solution is that entropy will decrease, right? If you put a future boundary condition on a problem, you get the entropy going the other way. we never do that. We only put initial boundary conditions on the problem. And so we see, oh, of course it has to increase. Given an initial boundary, yeah. Given a final boundary, it goes the other way. So it's nice and symmetric. And then there's the argument that I think Doug has already countered, that people never use future inputs. But of course, oh, here, I put that in a different slide. People do use future inputs. When you do relativity, general relativity, people calculate close time-like curves and imagine, what would happen in this circumstance. They use using future inputs. When people do action extremization, even in classical physics, they're using future boundary conditions to constrain it. And the path integral uses future boundary conditions. You solve these things all at once, right? You say, okay, what is the history that is extremized when I solve this all at once? And that's what I'm doing in my research right now with these quantum circuits. I am solving these all at once. This is what I'm doing. I'm saying, okay, I know these little bits of information here. That's some information, but maybe there's something hidden here I don't know. Maybe I actually don't know the right description of what's happening on these wires. Maybe there's some hidden variables, lambda here. Could be, right? And I run over here and I say, okay, I run the circuit, I get my outputs, up, down, up, whatever. And I say, now I know some information about what happened here. Now it's like a jigsaw puzzle. It's like a Sudoku, right? It's like I have some data over here. I have some data over here. Let's put it all together and figure out what happened in the middle. And I'm trying to build up models that look just like this, where I can say, oh, now I know that this happened here, and this happened here, and this happened here. And I keep it all on the wires. And if I can do this, then instead of blowing up like 2 to the n complex numbers, and every time you add another qubit, your description of reality would only be linear. It would only go up by n. I add one more qubit, and I just have one more wire. I don't need all of this math to keep track of reality. Why do I normally need this giant wave function? Because in the story goes, I don't know how I'm going to measure it until I do. So I want to keep all options open. So I want to consider the possibility that I measure it in this basis, or that basis, or that basis. And so I need all these possibilities. That's what the wave function is. It's like a big lookup table. If I measure it this way, calculate it this way. If I measure it that way, calculate it that way. And so you need this giant wave function for all the possibilities. But reality is not so complicated. In reality, any given run of any given quantum circuit, there is exactly one basis that you'll measure it in. That's the only one we actually need to be represented in reality. All the others can be what ifs, right? Oh, but if I had done it that way, then I get a whole different solution. If I just change this one gate, I get a different solution everywhere, not just here, but everywhere when I do it all at once. That's the secret sauce. That's what lets it work, is that changing one thing, one place, you recalculate the whole circuit and you get a different story. And if you do that, there's hope, actually, good hope, I think, that we're going to get a story that fits on the wires and we'll know what's actually happening in between measurements. Yes?
Say, assume that the symmetric causality is happening.
Mm-hmm.
Does doing the measurements at the end of your experiment tell you what those hidden variables were?
Yeah, that's the idea. Is that when I get my outcome, I should be able to take all this information I knew at the beginning. I now know more information than I did before, right? I've learned all this information at the end. I know how these gates were set up. I know what basis I was measuring. I take all that and I use it to compute what just happened. That's the idea. There's no reason why it couldn't work if you're allowed future input dependence. In other words, if I change the basis of this one measurement, I have to recalculate the whole thing.
This is on another layer of like mystique, because then you have to explain a sort of physical mechanism to how this time travel works.
Yeah. You need a rule. You need like a rule. Ideally, it would be some sort of action style rule, but it already works this way by solving it all at once, because that's what you do for the action. So yeah, you would need like an action style rule to describe why it worked. But that's true for, you could have made the same argument for people postulating atoms. Like, oh, if you postulate atoms to explain heat, you'll need rules to explain how the atoms work, right? Well, yeah, you do. But that's okay. That's the next level down, right? Yeah, right. And I'm not saying this is the bottom layer, right? people like Casa are trying to figure out what space-time is made of. And so that would be another layer down beyond that. But I'm not down there. I just, okay, given space-time, given that this is happening somewhere and this is happening somewhere else, what's going on there and what's going on there? That's all I want to know. Is that too much to ask? Probably. I'll keep asking it almost. Brendan, yes.
Yeah, so I know a couple times you've said you've used the word like choice, or you get to choose something or what have you. But in this picture where like the future affects the past and then it affects these, variables, where exactly where does free will come in? Because it does seem to imply that there's some sort of like, how does my brain reach
Your
out?
brain's not on the picture here, right? Your brain is not on this picture. Your brain is outside the model. So whatever your brain decides, you're going to come in and your brain can choose where these go and what gates they are, what settings they have, and what preparation you use, what the inputs are, and what basis you're going to measure it in. And that's all from outside the model. That's an input. That's what I call an input.
But would
That's-
my brain be part of that model ultimately? Right.
Ah,
If I'm part of
not
so
this model.
how does my brain,
Not
since
this
my
model.
brain is based on quantum mechanical, these same effects, right? So how does that all work out?
Okay, well then you say, oh, I want to include me in the system. I need a much, much bigger system. And at that point, it's not going to be very successful. I don't think I'm ever going to be able to model your brain. But I could, in principle, say there is a model that includes your brain. And now there's something outside that. And something outside that is choosing how your brain is going to be prodded and poked and measured, right? And so those are the inputs now. And your brain is the response. And then you say, well, why not make it bigger still? Why not include the whole universe? What are the inputs now? And now the inputs, I guess, would have to be cosmological boundary conditions, like this low entropy condition of the Big Bang and all sorts of other things. So eventually you need an input to solve anything. You can't solve a model without inputs. And what the scope of your model is changes what those inputs are. So in principle, yeah, but I'm not going to try to model your brain. I'll let you ponder your brain and I'll ponder these quantum circuits.
But isn't that fate then, kind of? Not to belabor the point, but if we're saying that boundary conditions are ultimately what determine the entire evolution of the system, wouldn't that be almost kind of like superdeterminism in a way, in that it's
What's
it's
causing
determined
what?
by boundary conditions?
If you think it's the hidden things that cause your choice, then you would be that was the problem Bell got into. But I don't think about it that way at all. It's my choice that causes the hidden things, right? I'm causing the past. The past isn't causing me in these experiments. So I'm not fated to do anything. I can do anything I want, and what I choose will determine what these past parameters are. That's the picture. There's no fate but what we make.
Okay, Sarah Connor.
I'm glad you got the reference. There's another question here too, right? Yes.
Compared to the other model you showed.
Oh yeah, this one, the retrocausal model. Okay.
Like, we have A, B, and C over there, right? And we're fiddling with A, B, and C. We're the ones changing those three, right?
These settings, yes.
Yeah, we're the ones changing.
Right.
But in the quantum circuit, we're not really changing the output, we're just measuring.
Well, these aren't outputs here. The little a and the big A is an important distinction, very crucial distinction. Let's see here, little a and big A. Little a is my setting. Little b is my setting. That's how I'm going to measure it. I do absolutely have control over that. You measure a qubit, you can measure any orientation of the block sphere you want, right? That is totally up to me. The outcome, I can't control. I see it, right? So I'm not controlling these. I'm controlling the settings. That's what makes it retrocausal. It's not weird to have the outcomes correlated with the past. That happens all the time. It's weird to have the settings correlated with the past. That would be new. That would be it. That would be at the end of the day, if this was right, and people say, why is quantum mechanics so counterintuitive and illogical? It's because, well, you're used to thinking about your choices only mattering to the future, and you're wrong. And they matter to the past too. And so that's why it seems so weird. That would be the answer. It's not that because nature is really a giant Hilbert space, Maybe because we're wrong about, our intuitions about causality are wrong. Not our intuitions about locality. We could save locality and get everything back in space and time. That would be fun. Okay. I love talking about this. Come by my office or shoot me an email